Ladies and gentlemen, today I'm going to be talking about the development of the Tarantula curve. What? What's the Tarantula curve? Well, I think it's pretty exciting. It's something that my research group's been working on for a long time, and it's actually being implemented by a lot of different people, and it's helping them better design their aggregate gradation. The title of the talk is The Development of the Tarantula Curve. There's been a number of different students whose graduate research work has been on this topic, and a big thanks to all of them. Also, we've been funded and helped by tons of different people, by industry, by government agencies, academia groups. Thanks so much for all of them. But a special thanks to these two guys, Jim Shilstone Sr. and Dick Gaynor. Both of these guys paved the way for aggregate gradation. They convinced people it was important and showed people and were tireless in how they promoted and talked about concrete and aggregates. And without them, I wouldn't be here today, and this wouldn't have happened. So a big thanks to both of them. Here's an outline of my talk. Let's go ahead and get started. All of our concrete mixtures need to have workability, durability, and strength, at least some strength. But workability is pretty important. Workability, if we don't have it, we can't build anything. We can't construct our concrete. So it's pretty critical to get right. One way to try to get workability, it was something called optimized graded concrete. It's kind of crazy. The goal is to increase the amount of aggregate while you decrease the volume of paste. Paste is the binder in the water. Paste happens to be the most costly, the least sustainable concrete ingredient, and has the biggest impact on our durability. If we can remove paste from our concrete, we're going to get a better product. But can we remove too much? Definitely. Can we do the same procedure with just any aggregate? No. You have to know a lot about the aggregates, and that's what this kind of talks about. For example, for you visual learners out there, here are 5 different slumps. I know I've shown this on other videos, but I think it's so important just to show again. These are 5 different slumps of what's on paper to be the same concrete mixture. Okay? Same volume of cement, same volume of water, same volume of aggregates, but different proportions, different gradations of these aggregates. And we get totally different performance. Now, if we zoom in and looked at the surface of these concretes, again, they would look totally different. That means their finishing is going to be totally different from one another. Wouldn't it be good to be able to understand this so we could produce concrete that's easy to finish and easy to place? That means people wouldn't do things like add extra water or increase the paste content of their concrete. That's what we want. Concrete that just performs. It just does what you ask it to do. And in extreme cases, you can get segregation, horrible segregation, where the rock goes one way, the paste goes the other. This is not good. So why would you do this? Well, you can reduce costs. That is number one. We're talking real money here. You can improve the strength, you can improve the durability, the sustainability, and you can control your concrete mixtures. Control them. Really get a grasp of them and understand what they're doing. To do this, we're going to use a suite of tests to evaluate the aggregate gradation and its impact on the workability properties. It's going to provide simple tools to help us design our concrete. We're going to look at data from a wide range of concrete, from very, very low slump to very, very high slump concrete. It's really important. Look at a wide range of materials. Everything I'm talking about is on this website, optimizegraded.com. If you missed something, if you want more information, you want some details, you can get more information here. Here's an overview of what we're trying to do. We want to use workability tests that measure practical concrete. Like, can we place it? Can we drag it? Can we pump it? Can we vibrate it? Can we finish it? Things that matter. Not things like the slump test, just how far it falls. How does it really perform and what we need our concrete to do? Can it be used in the field? To do this, we're going to use a whole suite of tests. We're going to use the slump. We're going to use something called the box test, the ICAR Rheometer, some visual observations, something called the float test. That's useful for actual finishing. And then we're going to pump the concrete, see how it performs as well. Not all concretes are investigated in all tests, but things like flowable concrete are investigated in some tests, and some things like low slump pavement concrete are investigated in others. Let's get started. Paving concrete, for example, is very low flow stuff. Look at this. It's all piled up in front of a concrete paver. As the paver starts to go over the top of it and vibrates it, it comes out looking like this. Amazing. This is exactly what you want. Has almost no surface problems on it. Came out the back of the paver, and look at this. It holds an edge without any formwork. That is the beauty of a slip form paver, that you don't need forms on the side of the concrete. It extrudes it. But to get this to work, you need concrete with a window of workability. You need concrete that's workable enough so that it'll respond to a vibrator, but not so flowable, not so super flowable that it doesn't hold an edge. That would be horrible, right? If it fell over, you'd have to put side forms on it, edge forms, and that happens sometimes. But you'd like to minimize that. And this window of workability is really important. And to investigate it, we had to understand and think about, how does a paver work? We had to realize that the part of the paver that does the most effort of consolidation is the vibrator. So we needed to understand, how does the concrete respond to vibration? And then how does it hold an edge after you're done vibrating it? So we wanted a simple test. I'm a simple guy. I like things that are simple because they have a chance to work, that can measure the response of vibration of the concrete and the filling ability of the grout to avoid any internal voids, and the ability of the slip form concrete to hold a sharp edge and be cohesive. And the slump test doesn't tell us this. And to get this information, we developed the box test. This is a 12-inch by 12-inch by 12-inch box. It's got an open top and an open bottom, and it's two L's that come together, that are held together by these really expensive pipe clamps. Yeah, they're about 20 bucks. And what you do is you actually fill the box full of 9.5 inches of unconsolidated concrete, and then use a 1-inch diameter stinger vibrator. This is not a paving vibrator. This is like a bridge deck vibrator. You turn it on as you count to 3 as it goes in and 3 as it goes out. You immediately take the clamps off and you look at the edges and you look for honeycombing and edge slumping. And why do we do this? If it honeycombs, that means the sphere of influence, or the energy of the vibrator, was not enough to consolidate the concrete. We can see it. And if it edge slumps, that means the concrete was too workable, that once you take the edges of the box off, it doesn't work. Let's see it in action. Here it is. There's the vibrator. There's the box full of the concrete. Goes in for 3 and out for 3. And there it is, consolidating the concrete. And now we immediately take the pipe clamps off. We look at the edges. And we're looking for honeycombing. We're also looking for edge slumping. Let's look at honeycombing first, though. That looks great. That looks like the side of a pavement as you would go down the road behind a paver. It's exactly what it would typically look like. And that's what the box test is designed to do. The amount of energy that the vibrator puts into the concrete has been designed based on the volume of the concrete and the amount of time it's in there and the speed to be the same energy that a paver would put in the concrete, moving at a typical speed with a typical vibrator spacing and setting. Use this ranking scale. It's a visual ranking scale. 1, 2, 3, or 4, and you're looking for a 1 or a 2. You're looking for less than 30% overall surface voids in the concrete. You can also look at edge slumping. You can hold a straight edge up and compare and see, did it fall at the bottom, did it fall at the top, and you want this to be less than 1/4 of an inch. Remember, this helps you look at the window of workability. Here's one with no edge slumping, super straight edges. Here's one where the top is falling over. It's not as good. That's not what you want. It's too workable. So in summary, the box test examines this window of workability for concrete pavement mixtures. It's helpful when you design mixtures in the lab, when you're trial batching, when you're troubleshooting field problems, when you're measuring variation in your actual production. It's kind of like having a miniature paver. It's pretty cool. Let's talk about the float test next. This test is going to evaluate the surface finishability of the concrete. So what we're going to take, we're going to place concrete in 3 foot by 2 foot by 3 inch forms, and we're going to strike the concrete off. Strike it off with a 2x4. Then we're going to create 3 known 1 inch diameter and 1 inch deep holes. Then we're going to move the bull float over the top at a fixed angle and a constant speed. And we're going to measure the number of passes. How many times back and forth does it take to close the 3 holes and to create a smooth finish? It might be kind of confusing. Let's see it in action. There it is in the forms. Strike it off the top. Place and level the concrete. Now we're going to use a template. We're going to place 3 1 inch diameter and 1 inch deep holes in the concrete itself. Now we're going to use our float. We're going to trim the float so it only rides on the surface of the concrete, not on the forms. We're going to use a yoke in the back to hold it at a constant angle. And now we have marks on the sides of the forms. We're actually going to use a metronome. That's like a drum machine. It's going to beep, 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 and we're going to move the float forward and move it back so that we hit each one of the marks at each beep. And we're going to measure how many times does it take to go past, to fill in the holes and to make it a smooth surface. And we're only going to look at the center area right here. So we can see the first pass going across here, and this is the last pass once it's done. Let's see some examples. So here's an example of the holes closing. Here's what the hole started with. Here's 2 passes. After 4 passes, the holes are gone, and that's great. Why do we have these holes? Well, sometimes when you strike the concrete off, you pluck aggregates out, and it's the finisher's job to fill those spots back in. And here's the surface. We're looking at surface texture. Here it is. Again, we want a 2 or lower, less than 30% of the overall surface to have texture on it. We also use something called the ICAR Rheometer, developed at the University of Texas at Austin. This is like a calibrated torque wrench. It's got a vane that goes inside the concrete and spins around. Okay, it measures really cool, several important rheological stress information about the concrete. That's another thing that we use to feed into our rating schedule. We also evaluate our flowable concrete with a concrete pump. This is our Putzmeister TK50 concrete pump. And when you're pumping concrete, if the forces get too high, that's because there's too much friction between the pipe and the concrete. Or the concrete itself may resist the actual flow, and that's not good. The mixture could also segregate, and gradual segregation can cause pipe pressures to increase until the pipe jams. And sudden segregation causes very high and erratic pressures in pipes. We don't want these to happen. We want to be able to avoid them. We want to be able to see how does our aggregate gradation make these things happen? And what can we do to make them go away? To test all this, we made a pipe network where our pump piped concrete around this circle over and over and over again. Okay, there it is, pumping around and in. We also put pressure gauges at these 4 locations, 1, 2, 3, and 4. One's right out of the pipe, one's after a long spot part, number 3 is after a bend, and number 4 is after another bend. To measure the pressures at these points, we actually had to make our own sensors. We actually used a chamber that's filled with oil with this pressure sensor that's hooked up to it. It has a rubber membrane. This rubber membrane goes on the surface. We actually drilled a hole in the pipe, welded a nut onto the pipe, and we screwed this in. So this is inside on the surface of the pipe. This is flush with the surface of the wall of the pipe. We calibrated this with water. So if we knew the water pressure, we would know what the voltage signal was coming out of the sensor. This is what the data looks like at the 4 different locations. Sensor 1's the highest. That makes sense. It's right after the pump. We can measure this information and how it degrades as it leaves the pumping location. Pretty cool, huh? We also see a typical piston stroke. That's this pressure when the piston stroke is starting to move. And then this is as the concrete flows through the pipe itself, called the primary curve and the secondary curve. We get some really neat information out of this. Like, for example, when things start to segregate, the pressures, you can see the coarse aggregate coming out of here and being separate from the other materials. Our pressures start to look like this. They get really high and really erratic and really dangerous. Okay? We did this because we want to improve the safety on job sites. We don't want you to have to deal with this. So if we can design our concrete mixture so this doesn't happen, everyone wins. For example, if I use, this is 5.5 sacks of cement, this is a pretty low overall binder content. We had pretty high pressures and we couldn't pump it for very long. When we went to six sacks out of the same mixture, the pressures were lower and then they started to increase. When we went to 6.5 sacks, the pressure stayed low. This means as my paste content went up, it was easier to pump. And there's a lot of people that know this, but we're able to quantify it. Here's sand content. This is the amount of fine sand inside the concrete. We'll talk more about this coming up. And as the fine sand percentage increased inside the concrete mixture, again, it got much, much easier. The sensor pressures were much lower over time as you pump the concrete. Again, this is pretty cool data, pretty helpful to help us give people guidance on how to design their concrete mixtures. We evaluated over 650 different concrete mixtures with 13 different coarse aggregates, 4 fine aggregates. We looked at low to high workability from 0 inches to about 8 inches of slump. We looked at different aggregations, different paste contents, water cement ratios, and water reducer dosages. All of these things all fed in to this research. An important point, we used the workability tests to find how the gradation impacted performance. We were all about workability, okay? Because we know how to get strength. It's all about water cement ratio. We know how to get durability. It's all about air and water cement ratio, typically, and oftentimes SCM content. So we're focused on what we don't know. How does our aggregation affect our workability? This helped us establish limits and also give reasons why these limits exist. They weren't just somebody's ideas. We have real data behind them. And again, all of this information is summarized on this website, optimizegraded.com. Everything went in to produce something called the Tarantula curve. That's what I'm showing here. This is over $1 million of research that we can summarize on one curve. I think that's pretty awesome when you can simplify things that much. On this curve, on the x-axis, we have the sieve size. On the y-axis, we have the percent retained. And then we have these limits. Okay? And everywhere these limits are actually stated, we tell you what happens if you go outside these limits. We also have a check for coarse sand and what coarse sand means. We also have a check for fine sand and what fine sand means. And we find that a coarse sand and fine sand gives us much more insight than just looking at something called the fineness modulus. And you might say, why is it called the tarantula curve? Well, we think it looks like a tarantula. That's a big spider. We think these are the legs of the spider. This is kind of the head and the body, and this is the bottom part of the spider. And since we developed it, we can name it whatever we want. So why? Why are these limits there? Why did we do this? Let me tell you. Let's talk about each limit. These golden ones here are the ones we're talking about. And I say here, they decrease workability and they promote segregation when you get outside of these limits. Let me show you what I mean. So this is the sieve number. This is the percent retained. This is kind of like the same plot, but I've removed all the parts of the tarantula curve. I'm only showing one part of it. And what we did is we took a concrete mixture and we teeter-tottered it. As in, we modified it by either adding more coarse aggregate and less intermediate, or more intermediate and less coarse aggregate. We teeter-taught it back and forth, and we held our sand content constant. And we can see we have a range of good performance. Then we have a moderate. That's when we're getting near the edge. Then we have a poor. That's when it's no longer satisfactory. And we could find out that, for example, if we have on this one a lot of coarse aggregate, we got a poor performance. And that was when we had a very, very low amount of intermediate aggregate. But look down here. This one, when we have a very low amount of coarse aggregate, but we have a very high amount of intermediate aggregate, again, we got poor performance. But the ones in the middle, that's the sweet spot. That's when things got good. And notice, where does this limit happen at? 20%. As soon as we got above 20% retained, we started to have problems. Here's what the slump test data looked like. When we had high coarse aggregate, it just didn't look right. It wasn't cohesive. It started to segregate. It was a problem. When we got high intermediate, the mix got very, very low slump. And right in the middle, it was just right. Visual observations. Again, high amounts of intermediate looked like this. The intermediate almost looks like it's coming out. It's much more obvious over here in this coarse. Look at this. The coarse aggregate seems to be coming out of the mixture. That's not good. It's hard to finish that. This is right in the middle. That's what we want. Let's talk about valleys. There's a lot of people that think valleys in your aggregation are a bad thing. So we're going to start out with one mixture. And what's a valley? That's when you lose sieve size or even gets low. Here, we sieved or took out a certain sieve size and added the aggregates on the sieves adjacent to it. And look, it was still good. There was a huge valley. We removed the 3/8. We removed the aggregate size that most people complain about that the asphalt companies want. We took it out, and we still got good concrete. Let's take out more. We took out the 3/8 and the half totally. Now, I'm not recommending you do this, but I'm telling you we still got good concrete. But notice, we never went above the magic 20% line. And this is almost impossible. As you lose certain sieve sizes, you almost always go above the 20% line. And that causes workability problems. So the maximum boundary limit of 20% on the 3/4 inch and number 4 sieve was established because once we went above it, we started to get workability and performance problems. And we could do a double or a single valley, and it did not drastically change our workability as long as no coarse sieve size went above 20%. So this valley idea, I think it might have been useful, but I think it was indirect. It wasn't about the valleys. It was about when you pushed down in one region, you had to push up in another region. And it was the going above that was causing the problems. It's not the valley itself. It's the going above. Let's look at this middle region about the coarse sand. I say here it creates surface finishing problems, and it changes the cohesion in your concrete mixture. Let me show you what I mean. First, we had a concrete mixture that performed great, and look at this kind of strange shape. And then we actually sieved the same material, the mix design is exactly the same, but we sieved it so it was the perfect, ideal bell-shaped curve. There's a lot of textbooks and people out there that think the bell-shaped curve should be the best shaped curve it is because it should be the perfect packing inside the concrete. But the performance wasn't great. It actually had surface finishing problems. Let me show you what I mean. I'm showing this actual limit here of about 12%. Once you give above this, this starts to happen to you. Before finishing, it looks like this. Look at all those surface voids. And after 8 passes of finishing the surface, it still wasn't complete. It still had holes in the surface. This is not a good finishing mix. When you get too much of this number 8 and 16 in the mixture, it can cause problems. What we find is when it comes to fine aggregate, you need to think of it in 2 categories: coarse sand and fine sand. And I think this should make sense because when it comes to coarse aggregate, we think of it again as coarse aggregate and intermediate aggregate. Why shouldn't we do the same thing with the sand? And if we do, I think, some of our problems, some of the limitations that we run into sometimes with the fineness modulus and with some of our strange manufactured sands or other type of weird sands. I think we can figure them out. Let's talk about these sizes. The coarse sand first. So to understand and observe the coarse sand behavior, we sieved out the number 8, 16, and 30 out of the mixture, and we gradually added it back in to see what would happen. Let's see what goes on. So again, this is the sieve sizes over here. This is the percent retained over here. We tried to hold the other parts of the gradation curve as constant as we possibly could. And we varied the amount of this coarse sand. We teeter-tottered it up and down. And again, we found if we went above the limit, we got poor finishing. We were below it, we were moderate, we were okay. Then we have this great, the sweet spot. We have this moderate, and if you get too low, it has poor cohesion. What do I mean? Let's talk about finishability first. Again, once these values get too high, here's at 0 passes, here's at 8 passes, here's where it took 18 passes. If you have somebody on the surface of the concrete going back and forth, now, I'm not saying that you can't produce concrete above this limit. I'm not saying that at all. I'm saying the amount of labor that's required is excessive, and we shouldn't be requiring people to do this. We should design our mixtures to be within the tarantula curve so we don't have to go through this. But again, this example took 18 passes to get a satisfactory surface finish. Here's one with poor cohesion. What does that mean? Well, once you dump it in the wheelbarrow, it segregates. We have almost all coarse aggregate right here and almost all paste over here. The cohesion is awful out of the concrete mixture. After it comes out of the actual mixer, it just starts to separate. So for cohesion, a minimum of 20% retained on the number 8 through the number 37 analysis was needed. For finishability, we created a maximum boundary limit of number 8 and 16 of 12% on each sieve size. Again, that's the middle part of the tarantula curve. Let's move into the back part, the fine sand part. Again, we have boundary limits and we have an equation, we have a calculation you have to meet. And there's two different ones here. One of them for slip form pavement and one of them for flowable concrete. Okay? Slip forming and flowable concrete. They're both a little bit different. Now we did our same teeter-tottering. We have sieve size down here, we have percent retained over here, and we teeter-tottered up and down. We kept the percentage of intermediate and coarse aggregate the same, and we just changed the amount of fines up and down. And again, we see this window of workability, this really good performance, and then it goes to moderate and then poor and unusable. Same thing up above. You get too high, it goes to poor and then eventually unusable. So there's this sweet spot that you want to have for the aggregates. We looked at lots of different stuff. And again, if you just look at it, if you get too little sand in it, it's deficient. It looks like it's just paste coated the aggregates. And if you get excessive amounts of sand, it looks hairy. You can't finish it. It looks strange. And if you get just the right amount, it looks perfect, right in the middle. Look at the slump test. If you have deficient sand, it's not cohesive. It disintegrates. Yeah, that's a 6-inch slump, but that's not good concrete. That's not what you want. Excessive sand, it gets very, very stiff. And this is, again, right in the middle. This is exactly what you want. This window, this right in the middle. And that's what the tarantula curve helps you get. Right in the middle. It helps you stay out of this trouble. Segregation starts to happen too when your sand gets out of whack. When you get too much coarse aggregate over here versus all this paste. This segregation, this is very dangerous in concrete, especially if you try to pump it. Ultimately, this is pretty cool. If you plot the overall performance of the sand versus the amount of fine sand, you can see if you have too little, it's unusable. And then you get in this sweet spot, this kind of parabola, this kind of moderate to good range, and then it gets bad again. And these are 3 different sand sources, and they all perform really, really similarly. So we try to draw some general limits at 25% and 40% for these mixtures. So the distribution of fine sand can vary largely without really affecting the workability. And the volume of fine sand should be between 25 and 40% for flowable concrete and 24 and 34% for slip form. And the big difference is slip forming needs more cohesion. It needs to help hold that concrete together, help hold the edge together. So that's the tarantula curve. And that's the why. We went over all the parts of it. Okay? That's what it's about. So let's talk about its use in the field. We're very lucky where we've got some insights to this. In Minnesota, in 1996 and 1998, they tried to start to do optimized graded concrete. And here I'm plotting their sieves of their gradations that they used, okay, versus the tarantula curve. And you can see they don't match very well. They're all over the place. And their performance of their mixtures were all over the place. And that was between 1996 to 1998. But once you got to 2009, 87% of their mixtures were inside the tarantula curve. Why was this happening? Well, the contractors are smart people. They're using concrete that works for them, and they're not using concrete that doesn't work for them. So they're iterating on their own to the mixes that work, and they're throwing the ones away that don't. And they're meeting the tarantula curve. But guess what? In 2009, the tarantula curve haven't even been invented yet. By 2010, 98% of their concrete mixtures were meeting the tarantula curve. And they're doing this on their own through trial and error. Okay? Wouldn't it have been great, or isn't it great now that we have the tarantula curve that helps us know when we start to go outside these boundaries what might happen to you? Here's some other data. I'm showing the years on the x-axis, and I'm showing in the blue here the percentage of their mixtures that were inside the tarantula curve. And in red, I'm showing the IRI. This is the surface roughness of their concrete. And you can see that as they improved and went to get more and more concrete mixtures inside the tarantula curve, more and more of their mixtures had smoother surfaces. Now, there may be some other explanation to this, but this is at least a coincidence that as more and more of their mixtures went inside the tarantula curve, more and more of the mixtures became smoother. Minnesota contractors are producing gradations that fit within the tarantula and having great success with them. And they're doing this with trial and error with no knowledge of the tarantula curve at all. They're doing this on their own. And as more mixtures entered the tarantula curve, the smoothness of the pavement improved. And similar data is out there as available for both Iowa and Michigan. And if you have good experiences, I'd love to hear about it. Let's talk about other data. So the FHWA has this awesome mobile concrete lab. It's an 18-wheeler it's all about concrete. It goes out and tests and evaluates concrete pavements. And this is great data from Jagan, who's been very, very nice to share it with me. And this is an awesome program. They were out in the field and they were investigating paving. And they noticed in the box test, these mixtures were not performing well in the field. And they also noticed they had tons of voids, surface voids, and voids inside the pavement as well. Look at all that. That's a problem. To fix that, they have to add water and really work that concrete. That means it's not going to have the same durability. If you plot that same mixture in the tarantula curve, it was all over the place. It was out in like 3 different locations. And by bringing it back within, more success was had. Here's another mixture. This mixture, look at this edge. Let's see how wavy it is. That means it's starting to fall down. Look, it's very obvious here. And look at the box test. It was showing the same thing. The box test was telling you that this was going to happen. But look at the tarantula curve. It told you as well. They were high on the ½ inch. As soon as they actually reduced that down, they were able to get better concrete performance. Okay? So the tarantula curve has been used in lots of projects, actually 10 lane miles in Texas, at very, very low binder contents. The mobile concrete labs used it, and they've determined it was a useful tool to help them investigate their field performance. Oklahoma, Minnesota, Texas, and Pennsylvania, at least while I'm shooting this video, are all integrating the tarantula curve into their specifications to help them make better concrete. This is really exciting. Again, you can find lots more information on this website, optimizegraded.com. So in conclusion, the tarantula curve is a modified version of the percent retained chart, but it's got 2 additional checks. It's not just the curve. You need the checks as well for coarse sand and also fine sand. But based on the materials and methods in this study, the tarantula curve was established and reasons were given for each of the boundaries. And the field data shows that mixtures with improved smoothness also correlated to mixtures being within inside the tarantula curve. So again, there's the website, there's my email address, there's my website. May the force be with you. Produce great concrete. Thanks, everybody. Bye.